My name is Chris Barron, and I will be starting the presentation for Group 1's Stat 512 project presentation. So, our research here was focused on how does environment and management influence crop yield, and also crop production in general. So, obviously, we know that climate has a significant influence on crop production. Rain, temperature, all of these are going to really affect how crops grow and how well they grow. And this is becoming increasingly important and also apparent due to climate change. In addition to environmental characteristics, farmer management practices are also going to significantly influence production. So irrigation, equipment, the type of agriculture that's being done, these are going to have big effects on crop production. And so understanding these influences and how they affect crop production can help both farmers and also plant breeders make decisions in either their production or in how they're breeding plants. So the first part of this research is how does this look on the global scale? So can we use global weather data and global management data to predict the average yield in a specific country year pair? What variables are most important for these predictions, and are there any interactions between them? And then finally, what is the predictive accuracy that we can actually even achieve with this country level spatial resolution? So the data set used for this, it comes from the FAO and also the World Data Bank and includes 101 countries and 10 different crops, and it goes over 23 years. So we have two categorical predictors, area and item, so that's country and crop, and then four continuous variables, year, rainfall, pesticides, and temperature. And between these variables, we're representing both environmental and management variables. So the first test of this is a global F test just to see are any of these significantly explaining the variation that we see in yield. And what we see is from this is that it is significant, which means at least one of these variables is explaining a significant amount of the variation present and why. So the next step of this is to go into diagnostics. Are there anything wrong? Are we violating any of the assumptions in our model? And so the main assumption violation that I saw was with the constant variance. So you can see here from this top residual plot, there is definitely non-constant variance. And so I performed a Box-Cox transformation, and you can see that residual plot below, and it has mostly addressed the problem. It hasn't fully solved it, but it's done a very good job of reducing it. There was also an issue of multicollinearity between precipitation and country, and it was so significant that I actually had to remove the precipitation data from the data set. The next question that I asked was, is there a lack of fit due to year? So we're treating year as a continuous numeric variable, but if we think about it, we wouldn't necessarily expect there to be a linear relationship between yield and year, because the weather each year is probably going to change, and so we would expect maybe a non-linear relationship. And so the lack of fit test, our null hypothesis is that year does not show a lack of fit. It can be treated as a continuous variable. And alternatively, it shows a lack of fit and year should be treated as a categorical variable. And so here you have the reduced model and the full model. And what we see from the test is that it is insignificant conclusion. So it is okay here to treat year as a continuous variable. And in fact, there is a positive correlation between year and yield. The next thing that I looked at for this model was looking at the interaction of terms. So do any of these terms interact? I only looked at the first order interactions, and there were a total of 10 of them. And from the ANOVA, I found that 5 of them were significant, but I only chose to keep 3 of them, namely because if you look at the F values of the uh, x1 by x4 and x1 by x6 interactions, they're orders of magnitude smaller than the other ones, and they add a lot more complexity to the model. And so that's why I chose not to include those. Now we have this Box-Cox transformed model with our interaction terms. And so now I did advanced diagnostics, and I found that there were a lot of influential points in here. And so I tried to address that with robust regression. And what I found was, while it did somewhat address the problem, it didn't fully address it. And it was also computationally expensive. And so instead, I chose to just remove those influential points. So this data set had over 28,000 observations. And so removing 1,000 data points from that was not significant. Finally, I look to look at the accuracy of the model. And so this is the final formula that I used. And what I found is that the R squared is very high and the RMSE is relatively low. And also, they both have low standard deviations, which should suggest that the model is not being overfit. And so the conclusion is that we're able to accurately predict yield in a country level spatial resolution, and it's highly influenced by what the crop is and where it's grown. In addition to that, weather data and management data were also significant factors, and they have different influences depending on the crop. So there are interactions between management practices and weather data that are different between crops.
The research question I looked at was, do sun and rain have equal impact on crop yield? The predictors I used were temperature, rainfall, humidity, and sun, and my response variable was yield per area rather than just yield because of the range of areas in my dataset. For my initial model, I used a standard multiple linear regression model. I plotted the residuals against each predictor to validate linearity. I performed the Bruce-Pagan test for heteroscedasticity, and I performed the Shapiro test for normality. I also looked to see if there was any multicollinearity in the model by looking at the VIF of the predictors. The VIFs were all below 10, which proves that there's no significant multicollinearity in the model. However, the Bruce-Pagan test showed issues with non-constant residuals, and the Shapiro test showed issues with non-normal residuals. To remedy these issues, I used the Box-Cox model. I used the method of maximum likelihood to find the best value of lambda for the transformation, which was negative 0.15. I then rechecked all the diagnostics on the Box-Cox model, and I found that the issue of non-normal residuals was fixed, and that the issue of non-constant residuals was improved, but still below the threshold value. To look at improving the issue of heteroscedasticity, I used the advanced remedial procedure of weighted least squares. I plotted the R standard residuals against the fitted WLS model, and the residuals appear to be pretty constant across the range of fitted values. And this is reflected in the Bruce-Pagan test where the p-value is now above the threshold. However, the issues of non-normal residuals that appeared to be fixed in the Box-Cox model have returned in the WLS model because the Shapiro test is sensitive to outliers. To determine which model was the best to use for my hypothesis test, I used a tenfold cross-validation. The Box-Cox model had the lowest root MSE, around 0.85. I included a model summary of the Box-Cox model in the equation given by the model. I performed a GLT test on the Box-Cox model to determine whether a subset of my predictors could be dropped, namely temperature and humidity. I built my reduced model and my full model, and from the ANOVA table, I concluded that temperature and humidity cannot be dropped from the model that already includes rainfall and sun. I then performed my hypothesis test on the model, where I had my reduced model with the combined sun and rain predictor, and the full model with all the individual variables. And from the ANOVA table of the full and reduced model, I can conclude that sun and rain do not have an equal impact on crop yield.
Hi everyone, my name is Fanqi Wu. My research question is about how precipitation, temperature, drought, and COVID-19 affect the amount of harvested area of corn through 10 years in 4 different states. Our data downloaded from NOAA and USDA. The data cover Illinois, Iowa, Minnesota, and Nebraska from 2014 to 2024. The hypothesis, as my question is, we're looking for at least one of the variables has a significant effect on the amount of harvested corn area. Therefore, I have a full model and a reduced model. And for the full model, we can tell that state variable is a significantly relevant to the harvested corn area. In the reduced model, precipitation and temperature are significant. Um, Before I did quick scan of the two models, after I quick scanned the two models, I also checked their assumptions. Um, the full model made most of assumptions, but not independency and multicollinearity. So different with the reduced model, it does only meet the last two assumptions. Therefore, I did robust uh, test to modify the two models. After robust, I used JLT and cross validation to compare the two models, and both results are telling me that the fall model is definitely significant because the state. So keep that in mind. The harvested corn area are collected by each state. So there's obvious state variable should be highly relevant to the y variable here. Each state has different land areas. They have different management policy and maybe the market price for the corn. But we cannot ignore environmental factors as the reduced model told us participation, precipitation and temperature are significant to the harvested area of corn. So that's my study. Thank you.
Hi, everybody. I'm Jacob, and I'll be talking to you about our fourth questions on the effects of seasonal precipitation on wheat harvest efficiency in the top producing U.S. states. This is important because wheat harvest is not always, the amount of wheat harvested is not always equal to the amount of wheat planted. Sometimes this could be due to grazing, since plots can be used for livestock grazing if yield prospects are low, such as in Texas, but more broadly, it's due to drought and water stress. So precipitation in these two vital um, seasons of growth are going to be essential to determining the amount of harvest loss in a given year. So we looked at how precipitation and vital growth stages affected the wheat harvest loss from 1919 up to 2024 in Texas, North Dakota, and Washington. So our independent variable being the difference between the area planted minus the area harvested. Um, we looked at fall precipitation, which is a 3-month period, which needed to be lagged to match the following year's harvest survey data. Spring precipitation, also a 3-month period. And then, of course, state and year. And looking at some of these biplots here, you can see colors representing state. We see some important interactions in harvest losses over time, and in these two growing seasons um, on the plots on the right. So this is the final model we ended up with, which includes all four of our predictors, 3 interaction terms. We found little evidence of multicollinearity. We used Cook's distance to manually remove some influential points, which helped with model fit. Utilized box-Cox analysis, which suggested we just log transform our dependent variable, which allowed us to meet our normality assumption, passing a Shapiro's test. We still had some evidence of non-normality. However, a robust model did not help with that and reduced fit. We also applied k-fold cross-validation and found that this OLS model gave us the best fits and best RMSE. And we also utilized some model selection criteria, specifically AIC, which suggested we remove some interaction terms, also year, which was important to our research question, So these couldn't be removed, so we ended up keeping our most complex model. And you can see with these residual plots and the QQ plot that we are qualitatively meeting our normality assumption and heterostochasticity assumption. So the first thing is our global F test. Look at the linear impacts of these terms. We were able to reject this null hypothesis, where at least one of these betas, actually a couple, was not equal to zero. So spring and fall precipitation were significant, as well as seasonal precipitation interaction with these states. And year wasn't significant on its own, but it was significant when it interacted with state. Our next hypothesis was whether the marginal effects of fall and spring precipitation on harvest loss was significantly different. So our full model being our original OLS model and our GLT test, our reduced model setting these two coefficients as equal to each other, which ended up resulting in a negative results where we failed to reject our null hypothesis, which showed that these marginal effects were actually not significantly different. Doesn't mean they're not significant on their own. You just cannot conclude that one is more important than the other. Our next hypothesis was looking at the quadratic impact of spring precipitation. Based on some literature, we were able to predict whether or not a increase past a certain point of spring precipitation will lead to increasing harvest losses. So we added a quadratic term to a new model that kept our previous predictors, including the linear spring precipitation term, but added this quadratic term where that quadratic term was significant, which allowed us to take the coefficient of the linear term and the quadratic term to estimate at which point does spring precipitation need to get to before it starts resulting in an increase in harvest loss, and that is 13 inches, which is an important value that farmers can utilize for predictions and future research questions. So to summarize our project, we've been able to demonstrate that these temporal changes and climate conditions are, of course, important predictors of yield across multiple different crops. And these relationships vary globally on multiple different scales, largely reflecting the influence of local climate and local management practices, which allow you to identify, locations where crop yield is at most risk of poor management practices and of climate change. So being able to accurately predict these relationships will have significant implications for how agriculture will be affected by climate change. So thank you for listening, and we're looking forward to your feedback.